in one of the first lectures of the global distribution of chlorophyll concentration from space. So that was a composite of more than a decade of satellite measurements of ocean chlorophyll. So, like I said at the beginning, phytoplankton contain chlorophyll to perform photosynthesis. So we can use chlorophyll concentration of the surface ocean as a proxy for ocean productivity. And places like the North Pacific subtropical gyre or the Southern Indian Ocean have extremely low chlorophyll concentrations, and they're very low productivity environments. But places like the Ross Sea and coastal upwelling systems, like you can just sort of see the Arabian upwelling system here, those places are relatively high productivity, so they have high chlorophyll concentrations. And getting back to the iron thing, actually, you can see this is Kerguelen Island in the Southern Ocean. So that's basically a piece of dirt sticking up in the middle of the Southern Ocean. And whenever when the Antarctic circumpolar current goes past Kerguelen Island, it's always washing off a little bit of dirt, which is working just the same as dust to fertilise productivity. So that's why you see high chlorophyll around Kerguelen Island. You see the same thing around the Marquesas and the Galapagos Islands in the tropical Pacific. Okay, so I wanted to just explain to you a little bit about how we make these measurements from space so that you can understand the utility and perhaps the limitations of these types of data. Okay, so if we were to look in general at what a satellite observation system looks like, here's our satellite that has some sort of sensor on it. If we're going to measure a signal from the ocean, we need a source of energy to elucidate that signal. And for a lot of measurements, the source of energy is the sun. So, for instance, if this were a sea surface temperature sensor on this satellite, we'd be measuring the infrared radiation emitted by the surface of the ocean as a function of, or that infrared radiation is stimulated by light from the sun. And so this is just a general depiction of a satellite observing system. So we have a source of energy which imparts some sort of signal from the ocean, which is recorded by the sensor on the satellite. The satellite then transmits those data back to a ground station. So this might be at NASA, or we used to have a receiving station here. And then those data need to be processed from things like raw radiance to a meaningful piece of data like sea surface temperature or chlorophyll concentration, and then those data are disseminated to the oceanographic community, and we calibrate, or we develop the conversion from the raw data to the useful data is done by taking measurements from the surface of the ocean and matching them up with data from the satellite. So that's sort of a generic remote sensing system. Satellites to measure properties of the ocean can be deployed on two different main types of satellites, geostationary or polar orbiting. So geostationary satellites just sit very high above the Earth and view the same part of the Earth all the time, and the satellite's rotating with the Earth. So an example would be like weather satellites that measure or like track atmospheric properties. But most of the satellites that measure ocean properties are polar orbiting, which means that they're spinning going from the North Pole to the South Pole in an orbit as the Earth rotates around underneath the satellite. And so so you can see this purple bit here, as the Earth's rotating, the satellite sees a different part of the Earth, and over time we can build up a picture of the whole globe. Okay, so I'm going to talk specifically about measuring ocean colour, and I should say that gaining an understanding of ocean colour is also important for the assignment that the QMS students are going to do. So what we measure when we're trying to measure chlorophyll is we're basically measuring the colour of the ocean, so it's often called ocean colour satellite. So we're essentially measuring the greenness of the ocean. So if it's greener, there's more chlorophyll, it's more productive. But the raw data that we use to derive that greenness or that colour is the amount of light that's emitted at certain different wavelengths. So this illustrates that here. So this black box here is supposed to be our satellite. So we've got a source of energy from the sun. So that light or solar radiation that comes from the sun interacts with the atmosphere. Some of it is reflected from the surface of the ocean, and some of it actually goes into the ocean, interacts with the chlorophyll that's present in phytoplankton, has its spectrum changed, and then gets re-emitted. So the satellite is seeing all of these signals. It's seeing the light that's interacted with the atmosphere, it's seeing the light that's reflected from the surface, and it's also seeing the light that's gone into the ocean and interacted with the chlorophyll. We're not at all interested in this red stuff, the atmospheric signal, and we're not interested in the light that's just been reflected from the surface of the ocean because it hasn't interacted with the chlorophyll in the ocean. What we're interested in is this blue part here, which is less than 10, probably less than 5% of the actual signal that we're seeing at the satellite. So we have to get rid of all this atmospheric and reflected glint before we get to the stuff that's interesting. So what remember I showed before that chlorophyll absorbs strongly in the blue, a little bit in the red, but it doesn't absorb at all in the green. So if we measure the amount of green light that's coming out of the ocean and the amount of blue light that's coming out of the ocean, we can get an idea of how much of specifically that blue light has been absorbed by chlorophyll. And that's essentially what we're measuring here. We measure any one of these wavelengths that's in the blue, and we divide that by the amount of light in the green. Then we plug that into a complicated algorithm that we developed from taking thousands of measurements of chlorophyll in the surface waters of the ocean, and then we can get a chlorophyll concentration from the satellite. Now, one of the things that I'd like you to understand is the limitations of this. So this chlorophyll algorithm is only as good as the data that go into developing the algorithm. And probably, more than half of the data that went into this algorithm came from places like the North Atlantic or the tropical Pacific. Very little of the data that went into making this algorithm came from the Southern Ocean, for instance. And so I had a student, Rob Johnson, who looked at how good these satellite algorithms are for the Southern Ocean, and it turns out that they're pretty crap. So the chlorophyll concentration from satellites is underestimated by about 70%. So if you were to plot satellite chlorophyll versus in situ real chlorophyll, the slope is about 0.3. So the satellite is dramatically underestimating the chlorophyll concentration. So what Rob did was took a bunch of in situ measurements of chlorophyll from the Southern Ocean, and he basically made a better chlorophyll algorithm. And so now we've got chlorophyll data for the Southern Ocean that aren't significantly underestimated. So that's one potential limitation. So this is how this is made. This algorithm is made. So here we've got our ratio of 490 to 555. So it's basically that ratio of blue to green. And we fit a line through this cloud of points here, which is the chlorophyll concentration versus that ratio. And that's what gives us this algorithm here. So you can go, and in the lab today, I'm going to explain where we get these ocean color data from. But you can go to the NASA website and you just download these global maps of surface productivity. Or surface chlorophyll concentration, sorry. So this is there was a sensor that was launched in about 1978 that was sort of a proof of concept. It was the first satellite that measured surface chlorophyll concentrations. It was heavily focused on coastal areas. Then in 1997, this satellite CWIFS went up, and it worked. It was supposed to work for a couple of years. It worked until about 2010, so it worked for about 13 years. And it was the most successful chlorophyll measuring satellite that we've ever had, really. So this is what I mentioned, that the satellites are polar orbiting, so it's going from the North Pole to the South Pole as the Earth rotates around underneath the satellite. And so it has these swaths that you can then stitch together, and this is what the CWIFS satellite sees in one day. And notice that we can't measure, there are some parameters for the ocean, like microwave sea surface temperature, that we can measure through clouds, but we can't measure chlorophyll through clouds because it's an optical measurement. So that's another limitation of the data, especially in the Southern Ocean. It's a really, it's really cloudy, so it's hard to get good data. But what we can do is go from one day through to weeks or months, and this is a satellite composite for summer in the Northern Hemisphere. So you can see a lot of ice around Antarctica because it's Southern Hemisphere winter. And you can see the spring bloom in the North Atlantic. So that's what Strutton studied when he came up with his critical depth hypothesis. So if we stitch enough days or months of data together, we can get rid of most of the clouds and get a global picture of chlorophyll concentrations, which we use as a proxy for phytoplankton productivity. Okay, so this just illustrates, so this is for the west coast of the US, and which is a notoriously cloudy area as well. It's a period of a place of active upwelling. So you've got cool waters coming to the surface, which make a lot of clouds. So this is what one day looks like for the west coast of the US. If we then stitch together 3 days, we fill in a few of those cloud gaps. If we then stitch together 8 days, we fill in a few more of those gaps. And then if we went to more, went to a month, we'd probably get rid of a lot of those gaps. But a limitation is, this is all well and good. You can stitch together as many days of data as you like, but you always need to remember that, although this is an 8-day average, any one of these valid pixels could have had 1 day's worth of data or 8 days worth of data that went into it. And so it introduces a temporal variability into your interpretation of chlorophyll patterns. So here's a particularly rare non-cloudy day off the coast of Oregon and Washington. On the left here, we've got sea surface temperature. On the middle panel here, we've got chlorophyll concentration. And on the right here, we've got chlorophyll fluorescence. So we're getting the chlorophyll concentration from basically the color of the water, so the ratio of those wavelengths. But when, this is true of all photosynthetic organisms, when they absorb solar radiation, some of that energy is put into photosynthesis, but some of it is re-emitted as heat or as fluorescence. And depending on how healthy the cells are, if the cells are very healthy, they're probably going to be able to push more of that energy through into photosynthesis. If the cells are compromised in some way, maybe through iron limitation, then more of that solar energy is going to be given off as fluorescence because they won't be able to shunt it through photosynthesis. So here we see, this gives us an idea of like how many phytoplankton are there. This fluorescence image on the right-hand side might tell us something about how healthy they are. If they're giving off a lot of fluorescence relative to chlorophyll, they're probably not very healthy because they're not being able to put that solar energy into photosynthesis. And so there's an example here where we've got relatively low chlorophyll, we've got a lot of fluorescence, so that means that the cells out there are probably nutrient limited away from this active area of upwelling. So this is a coastal upwelling system, so we get very high chlorophyll near the coast in the summertime. So this is, I was talking before about the CWIF satellite. This is another satellite, MODIS, that went up in 2002, and it's still operational today. It overlapped for a few years with CWIFs, but it had this extra channel on here that CWIFs didn't have. It has something that can tell us something about not just how much phytoplankton are there, but how healthy they are, or how their physiology is performing. Okay, so just to, I'd like to sort of give you this information if you ever have a use for satellite chlorophyll data in your work. I mentioned the Coastal Zone Colour Scanner. That was a mission that was sort of put up as a proof of concept, and it didn't measure the open oceans very well. But then in 1997, we had CWIS, which was super successful. Then MODIS launched in 2002. There was a European sensor that operated for about 10 years. And for a long time, NASA was like the main player in terms of putting up ocean colour satellites. That's becoming less so now. They have a mission up right now called VEERS, which is sort of much hated by a lot of the ocean colour community because it's not very well calibrated. But those data are available. Now we're entering an era where countries from Asia and Europe are more bigger players in terms of putting up ocean colour satellites. So we need to get friendly with them if we want to download data for free. Okay, so I'm just going to close. Yeah, it's got a couple of minutes. Going to close with some information about today's lab. So I've been talking a lot about the delivery of nutrients to the surface waters and uptake of those nutrients by phytoplankton. I've been showing you, observations of global maps of nitrate concentration, for instance. So one of the goals of oceanography is to formalise our understanding of ocean processes in models. And we do that for several reasons. We want to understand how the system works, but we also use models to perform experiments that we can't do in the real world to try and understand the important processes that are regulating ocean productivity. So what we're going to do this afternoon is mess around with a very simple model that relates the uptake of nutrients by phytoplankton with grazing by zooplankton and remineralization of those nutrients. So we're going to run a MATLAB model that describes the variability of phytoplankton, zooplankton, and nutrients. And this just shows the important processes that we're going to study. So we're going to parameterize the change in, or the variability of the phytoplankton community as a function of how much nutrients they're taking up, how fast they're dying, and how fast they're being eaten by zooplankton. We parameterize the change in zooplankton as their growth efficiency times the rate at which they're eating phytoplankton and how fast they're dying. And then we can calculate the change in nutrients as the loss term for that is nutrient uptake by phytoplankton. Then there's the remineralization of phytoplankton by grazing, the amount of phytoplankton that get remineralized just from cell death, and the amount of zooplankton that get remineralized just from them dying. And we can formalize that in a series of differential equations, and that's basically what the MATLAB code's going to do for us. And we're going to investigate what happens when we do things like, so this VM here is the uptake rate for nutrient uptake. So we're going to do things like change the nutrient uptake rate. We're going to change the amount of mixing that delivers nutrients to the surface. We're going to change the amount of the death rates of zooplankton and phytoplankton, all using these equations. So I showed you in that plot there how we parameterize the uptake of nutrients, and that's shown in this plot here. So on the y-axis we have the uptake rate, the nutrient uptake rate by phytoplankton, and on the y-axis, x-axis here, we have the nitrate concentration. So this looks fairly similar to the curves that I was showing you for photosynthesis, where as we increase light, the photosynthetic rate increases. So this is just saying the same thing. As we increase the nutrient concentration, the uptake rate by phytoplankton of that nutrient increases. The shape of this curve would be different for different species of phytoplankton, and the shape of that curve is defined by two parameters. One is the maximum uptake rate, Vmax here, and the other is what's called the half saturation constant. So that's the concentration of nutrients at which productivity is half of the maximum. And this is these curves are sometimes referred to as monod relationships or Michaelis-Menten uptake kinetics. And one of the things that we're going to do is look at what happens to phytoplankton productivity and the interaction with zooplankton when we vary this parameter Vmax here. So what this is basically showing is that if we start out at 0 nutrient concentration and we start to increase the concentration of nutrients, phytoplankton will respond by taking up more nutrients or taking up nutrients more rapidly in a linear fashion, much like they did in the photosynthesis curve. But then they'll get to a point where if you give them more nutrients, they just can't take up any more nutrients. And this would be an example of why this might happen is that a phytoplankton cell is only so big. Many phytoplankton have active transporters to get nutrients outside of the cell into the cell. And when you get to a point that those transporters are saturated, you just can't get any more nutrients into the cell. So if we were to compare two different types of phytoplankton, so let's compare a diatom that might be growing in a coastal upwelling system with a very small cyanobacteria that's growing in the subtropical gyres. The phytoplankton that live in the subtropical gyres tend to have very low half saturation constants. So they are approaching their maximum uptake rate of nutrients at very low concentrations. Whereas diatoms in a coastal upwelling zone are accustomed to having nutrients actively upwelled. They're accustomed to high nitrate concentrations, so they're probably going to have a higher half saturation constant and probably a higher maximum growth rate. And so I've just got a couple of little example of that over here. So I've just drawn these, forget about the top one here, I've just drawn these two curves here. So this curve here where the uptake rate increases very rapidly at low concentrations and then levels off at a pretty low maximum rate, that might be an example of a small phytoplankton cell that's accustomed to low nutrient concentrations in the tropical Pacific, the subtropical gyres, whereas a coastal diatom is probably going to have a higher half saturation constant, that's this value here, but it's probably going to attain higher uptake rates or higher growth rates as you give it more nutrients. So one of the things we're going to explore today is how those different uptake rates influence the behaviour of the system. Okay, so I think I'll leave it there. So, Melissa, we were going to start the lab at 1:30, is that correct? Or? Yeah, okay. Yeah, okay. So let's just convene in the computer lab at 1:30.